Welcome to the next video in the mathematical logic series, this time talking about properties of sequence. Let's recall that a sequent is a pair. In particular, it is a pair where the left coordinate is a set of formulae, the right coordinate is some formula, and in particular, it is a pair that comes from our derivation system, right? So some pairs are not, but the ones that we call sequents are pairs that were produced by the deductive system that we talked about in past videos. When we talk about a property of a sequent, basically we are talking about some property of x and alpha. So let's just give an example of some such property, right? Just a property that can be enjoyed by some set of formulae and a formula. Well, one property that we've already studied previously is the entailment property, right? That's a relationship between these two. And it's the relationship that, x entails alpha, which recall is every model satisfying every sentence or every formula in x also satisfies alpha. So that is a property of the pair. And so we could say that that is a property of the sequent. Now, I want to talk about a feature that some properties may have, namely preservation under some rules. So suppose that we have some rule. This could be a rule like any of the ones that we've discussed earlier, where you have some collection of sequents all above a vertical line, a horizontal line, and below it some other sequent. And we are saying that the rule allows, right, the rule says that whenever you have the sequence above the line, we also have the sequent, right? It is something derivable in our proof system that the sequent below is accepted as a sequent. So let E be a property of sequence with the feature that every time the sequence above this rule, right above the bar, when all of those sequents enjoy the property E, then also the sequent below the bar also enjoys the property E. So we will say that E is closed under this rule R. Now, if we think about any property E which has this feature, then notice that what this entails is that every sequent of the form alpha alpha must have the property E, because there's nothing above the bar, and so the condition that everything above the bar has property E is satisfied through vacuous quantification, and therefore every alpha v dash or turnstile, or however we want to pronounce this symbol, but right, so let's recall here. Let me get rid of this. Let's recall how that rule looked, right? This was our rule, initial sequent. And so since alpha could be anything, then every sequent of this form is a sequent in our deductive system and has the property E if E is to be preserved by all of our rules. Now consider any other sequent that is derivable in our system. Then there must be some proof using the rules from an initial, right, something like initial sequence, some collection of initial sequence, eventually building down to this particular sequent that we derive. So again, if we're imagining that E is some property which is preserved by all of our rules, then anything that is provable, it satisfies the initial sequence, which make up kind of the leaves of the tree in our tree proof, and then are preserved as you go down the tree and must be preserved all the way down until you reach this sequent which is provable in our system. So in effect, what I am getting at, the point of all of this, is that a property preserved by all of our rules is therefore enjoyed by every sequent provable in our system. So I bring all of this up because it is in service of a very fast proof of the soundness of our proof system. So let's recall, I've discussed this much earlier, but it bears repeating. What is soundness? The sort of what I like to tongue-in-cheek call a communist slogan for soundness is that everything provable in the truth system is true. Now, more rigorously, what that means is that if X turnstile alpha is a sequent in our proof system, then X satisfies alpha, or entails alpha. So that's the property of soundness, that a syntactic derivation always means that the proof is valid in effect. All we have to do is prove that this property, right? We've already said that this entailment relationship is a property of sequence. So all we have to do is show that this property of sequence is preserved by all the rules. And that's a very easy check. I mean, after all, take for instance this alpha turnstile alpha. Well, whenever that is true, right? We just know that we always have alpha double turnstile alpha, right? That is just extremely easy, trivial, really, to show that that is true. And so the entailment relationship is preserved by this rule. And then you can take any of the other rules and show that whenever the sequence above the bar enjoy the property, which is to say that the entailments hold, then the sequent below the bar also enjoys the property, which is to say also entailment holds there. So you just go through all the rules, make fairly trivial proofs in every single one of them, and you see that E is such a property, and therefore this entailment relationship holds for all sequence. And that's the proof of soundness, right? So it's one of our big theorems, and it has this sort of amazingly simple proof. Finally, as a point, I'm not going to prove it. It's a fairly easy proof, kind of just goes the same way that we did the previous proof for soundness. But we could state the following claim that if X turnstile alpha, right, if X proves alpha, then there is some finite subset of X which also proves alpha, right? And this just seems intuitively clear, right? Because proofs themselves are finite and can really only make essential use of finitely many elements of the set. That's not a rigorous proof, but that's just the intuition. In any case, a rigorous proof can be given by showing that this property of there being some finite subset, you can do this using what we just showed, which is that if the property is preserved by all the rules, then every sequent has it. And by the way, that sometimes goes by the name of proof by sequent induction, or induction on sequence.